This is our last chapter. It's on solutions. Chapter 13 is on pure solids, and that's not in our syllabus, so we're moving on to our last chapter, 14. And solutions involve dissolving one thing into another, and we always want to know if something's going to be soluble when we add it to water or some other solvent. And solubility is a concentration term. It's the maximum amount of solute that will dissolve in the solvent. It's the concentration needed to achieve saturation. So sodium chloride, you think about sodium chloride as being soluble in water, but you can dissolve 35.7 grams, which is quite a bit. Up to that amount will go into solution, and anything above that, it would just sit as a precipitate in the bottom of the flask or the beaker. So it's a concentration term. How many grams will be in how many milliliters. Sometimes you see this given as 35.7 grams in 100 grams of water, but pretty much the same thing. Okay, so for the last chapter, we saw that there were different types of interactions. First one is a London dispersion reaction between nonpolar molecules or between atoms that are neutral. The dipole, here's an example of acetone, like methyls, and then there's a carbon and then an oxygen with chloroform, which is like methane. There's 3 CCl groups and then a hydrogen, so they're both going to be polar and they're interacting with each other. Here's ethanol and water interacting. You get the oxygen on the water interacting with the hydrogen on the ethanol because it's a carbon, oxygen, hydrogen structure. This one we didn't look into, but this is about dissolving solids, neutral solids in solvents, ion dipole. All right, anyway, this is similar to a slide that we looked at in the last chapter where we looked at the water and hydrogen bonding. So you have the oxygen, hydrogen, oxygen, hydrogen bonds, oxygen, hydrogen, oxygen. And this one is hydrogen, oxygen. Okay, oxygen, hydrogen, oxygen on that one. Yeah. Anyway, so there's 4 for water, 4 hydrogen bonds in methanol. You have 3, and one of them is not illustrated here. The third one should be right here. But this is CH3OH for methanol. And this particular methanol can hydrogen bond here, and then there should be a third one there. So a total of 3 hydrogen bonds. This is octane on the right. And it's got 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. I like this figure because it shows how they stack together. There's a fairly strong interaction, London dispersion force between them because the molecule is getting rather large there. So there's a pretty strong attraction to other octane molecules. Okay, and this one you've got liquids dissolving in other liquids. So is methanol soluble in water? And the answer is yes, it's 100% soluble. And then this table is telling us that as the carbon chain length increases, the solubility decreases. So maybe I could draw a few of those so you could see that. Just got my cough drop here. Excuse me. Okay. So methanol, I don't have to draw the whole thing out, but you get a little bit of a sense of it. That's methanol. Ethanol is so these OH groups, this makes the molecule the alcohol. Propanol has 3. Oh, I guess they don't. Yeah, propanol's in there. Butanol has 4 carbons. pentanol, and then hexanol. So let's look at hexanol. 1, 2, 3, 4, 5, 6. OH. More like a Lewis structure, but in fact it's bent. So if you compare, let me erase that middle one there. Excuse me. So if you compare these two molecules, you can see that this part of the molecule is polar, this part of the molecule is nonpolar. So this is going to have a high probability of dissolving in water. It'll just hydrogen bond to water. No problem. And there's 2 lone pairs on the oxygen. So, but this one is different. Hexanol, you have 6 carbons. So this whole part is nonpolar. And then this little part here is polar. So what we're going to find then is that these hexanol molecules want to stick together, basically. And then these little OHs coming out the side. I mean, they will interact with water somewhat, but not too, you know, when you look at the entire volume of the system, the OH part is pretty small. So this, let's see what it's in the table. A little tiny bit, 0.6 grams will dissolve in water, but the majority of it will not. And that's for that reason. So we use that term like dissolves like. Molecules that have similar intermolecular forces will stay together. There's stability associated with that. And then in the top, you see that polar molecules stick together as well. The issue then becomes, you know, if you have pure water, you have to break those hydrogen bonds. If you have pure methanol, you have to break those hydrogen bonds. And then when they interact, the new hydrogen bonds that form have to be similar. And in this case, they are, but in this case, they're not. So that's another way to look at it. All right, now here, I've actually deleted quite a few slides from this chapter to kind of simplify it. But one of the main things we look at in this chapter is concentration terms. And I'll walk you through this. You know about density. You've been practicing density problems for a very long time. Mass divided by volume is density. Molarity we have used in this course already. Moles of solute divided by liters of solution. So some new ones are molality. So I'll see the similarity in the spelling there. And we use lowercase m instead of capital M. The numerators are the same, moles of solute. Here it's divided by liters of solution, and in this one it's kilograms of solvent, which would be water for the most case. So if I said I had a 2.0 m, if I had a 2.4 molal solution versus a 2.4 molar AR, right? A 2 molar solution or a 2 molal solution. This means that there are 2 moles of whatever it is, sodium chloride, whatever the solute is, and then it would be divided by 1 kilogram of water. In this case, it would be 2 moles sodium chloride divided by 1 liter of solution, where the solution is the combination of sodium chloride and water. So it just depends. You'll see in this chapter there's applications for molality. All right, so, but it's strange because we use a little m and we say molality, and then we can say a 2.0 molal solution. So it's similar to molarity in that sense. The sense of the use of m is a little bit different. So it's okay though. All right, mass percent is next, and this one you've probably worked with in the lab. So this one you have your solute, and you have the mass of it, and you're going to divide by mass of solution. So if I had like a 20%, let's say I had a 20% by mass solution. This means I've got 20 grams of whatever it is, sodium chloride, divided by 100 grams of, solution, not water, solution. So that means in this one, if I have 100 grams of solution, and that's times 100, then I have 20 grams of sodium chloride and 80 grams of water. All right, and then there's 3 parts to this. This was actually a separate slide, but I moved it up. So this should be here instead of this shorter version of mass percent. So come down here. This is what we just said. Mass of the component in solution divided by total mass of solution. So that would be this one. But when you dissolve things, sometimes, especially with gases, you can have very, very small concentrations of the solute. And so if you had 0.00002%, then you might think of a different way to say it than just multiplying times 100 and saying such and such percent. So it can be that it's very small, and it may be practical to multiply times 1 million to 10 to the power 6. And then if it's 1,000 times smaller than that, it's very small, and it's going to be parts per billion. So the first one is parts per million. This one is parts per billion. If you have very small quantities, you just multiply times the numbers here. And then you'd say, okay, I have a 50 part per billion. That means 50 times 10 to the minus 9%, right? So I'm not going to worry about parts per million or parts per billion for Spring 20 Chem 101, but we'll leave it in there just to be complete on that subject. And you've heard of it, right? All right, and then the last one is mole fraction. We looked at this in the gases chapter. So this is moles of A divided by the total moles here. Moles of A divided by total moles. All right, so we want to be able to go back and forth between some of these. Focus on the ones that are here. We've got density for these 3 solutions of HCl. And we want to look at molarity, molality, mass percent, and mole fraction. All right, so there are 3 solutions, 1, 2, and 3. And these are the densities in grams per milliliter. So the first solution has 1.2 grams per milliliter, and it's a 3 molar solution. With this information, can we calculate the remaining 3? And then you have solution 2, which has 0.8 density. And we know the molality. Can we convert back to these? And third one as well. It's in terms of mass percent. So it's just an exercise to go through. And a little complicated, so I'll start with a clean whiteboard here. So I'll number them. The first one is going to be, solution 1. And we're just going to do it one step at a time. The first thing we want to do is take 3 molar solution, 3 molar concentration, and convert it to molality. So as we just talked about, we know that the units for molarity are moles per liter of solution. And for molality, it's moles solute. Divided by a kilogram of water. So, since you have 3 molar solution, I say one way to solve this problem is to look at the denominator here and say, okay, well, what if I actually had 1 liter? If that's the case, then I have 3 moles of HCl. Okay, so you got some information there. Now you can go to the mass of HCl using molar mass. So that one will be 3 moles of HCl. Use the molar mass 36.45 grams per mole. 109.35 grams HCl. Okay, next thing you can do is get the mass of the solution. And you take the 1 liter of solution, which was the assumption. And here you should go 10 to the 3rd milliliters per liter. Now it's in milliliters. Use the density of the solution, which is 1.2 grams per milliliter. And then go back to kilograms, so 1 kilogram for every 10 to the 3rd grams. And then this works out as 1.2 kilograms, or you could write it as 1,200 grams. So if you know the mass of the solution and the mass of HCl, you can get the mass of water. 1,200 grams minus 109.35 grams. And that is equal to 1090.65 grams, which is about 1.09 kilograms of water. Okay, so we got that. And then put it all together. Molality will be 3.0 moles of HCl. And divide that by 1.09 kilograms of water. And that is 2.8 m. So we started with 3 molar solution and we ended up with a 2.8 molal solution. Those numbers are pretty similar, and that's because the solution is dilute and there's not a lot of difference between a kilogram of water and a liter of solution, since the density is practically 1. And you know, the solution is dilute, so it's like water itself. Okay, so that's the first one, and we're still working on solution 1. Now we want to take, let's do a different color here. Now we're going to take our 3 molar solution again and go to mass percent instead. We've got all the information. This is going to be equal to the mass of the solute divided by mass of the solution times 100. So mass percent by mass equals 109.35 grams of HCl. And you divide that by 1,200 grams of the solution. So this is equal to 9.1%. Okay. So then the third part is to go 3 molar to mole fraction. And this will be equal to moles of HCl divided by moles HCl plus moles of water. So we know the moles of HCl, but we don't know the moles of water. So let's get that first. Moles H2O equals 1.09 kilograms water times 10 to the 3rd grams per kilogram, and then divided by 18.02 grams per mole. So you got 60.49 moles H2O. Alright, so then mole fraction of HCl is equal to 3 divided by 3 plus 60.49. And that is 0.047. You do not multiply the mole fraction by 100. Just leave it as a fraction instead. If you wanted the mole fraction of the water, it would be 60.49 divided by 3 plus 60.49, 0.95. This is 0.05, right? The sum of those two is equal to 1. All right, so that is the first one. And then we'll start a new one page for the second one. So the solution 2 has density 0.80 grams per milliliter, and we are given that the molality is 0.020. All right, I think we can do that. So the trick here is to remember that molality is moles solute divided by kilograms of water. So again, second time I showed this to you, I look at the denominator and say, okay, what if I had one of those? So if I had 1 kilogram of water, then I have 0.02 moles HCl. That pretty much solves the problem there. All right, now, if you use the density, let's see where we're going with this now. We've got the moles of solute, and we're going to go to molarity. So we're going to go molar to molarity. And again, you got moles solute, kilogram water. You're going to go moles solute to 1 liter of solution. So we've got to get the mass of the HCl, add that to the mass of the solution, then use the density to get the volume of the solution, and then that should be in liters for the denominator right here. So a couple of steps. We've got the moles already. So let's get the mass of HCl, 0.020 moles HCl. Don't need to do that. Times 36.45 grams per mole. So this is 0.73 grams of HCl. So the mass of the solution equals 1 kilogram, which is 1,000 grams, plus 0.73 grams. So you have 1,000.73 grams of solution. Okay, and then take that mass and go to volume of the solution. 1,000.73 grams. And you have 0.080 grams per milliliter. So you're dividing by the density. And then 10 to the third milliliters per liter. This works out to be 1.25 liters. So 1 kilogram of solvent, but you get 1.25 liters. All right, and then next is put it all together. Molarity is going to be equal to 0.020 moles of HCl divided by 1.25 liters of solution. And that is 0.016 molar. Okay, that's the first one. Second one, go from molality to percent by mass. And for this one, percent by mass will be equal to 0.73 grams HCl divided by the total mass, which is 1,000.73 grams of solution, times 100 equals 0.073% by mass. All right, then the third one, we're going from molality to mole fraction of HCl. And we have, let's see here. We need to get the mole. So this is the ratio of the moles of HCl divided by moles. We know the moles of HCl already, right? 0.02. But we need the moles of water. And if you have a kilogram of water, you can go to moles from that. So here you want to get moles water. And so we do 1 kilogram of water. Go from kilograms to grams. Then you got grams, you want to go to moles. So 18.02 grams per mole for H2O. And this gives us 55.5 moles of water. All right, now we got it all. So the mole fraction of HCl will be 0.020 moles of HCl divided by 0.020 plus 55.5. So the sum of those two is the moles of the solution. This is 0.00036. And then moles of water, 55.5 divided by the same thing. And that is 0.99964, which is approximately 1. So, if you had enough sig figs, you could say 1 minus 0.00036 is equal to this, but in the end, you probably end up with 1 or 0.9999, which is fine. This is the one we're usually interested in anyway. Okay, so that's 2 of the solutions. Usually I let the students figure out the third one, but the way this is set up here, rather than going back and forth, I'll just go ahead and do it. It's the end of the semester, you probably don't have time to ask me for it anyway. So solution 3, then you're going from percent mass to molality as your first one. This is percent mass, and you're going to do all 3. So for this one, remember the definition is mass of solute divided by total mass of solution times 100. So that's that. And again, what I do is assume a certain amount of the solution. So I say assume 100 grams solution. Then, I forgot to give this to you. This is, 20% by mass of HCl. So then you have 20 grams of HCl. All right, and you can go through the details on that. You can calculate from here. You can go to moles using molar mass, and you've got 100. So the moles turned out to be 0.549 moles, and then let's see. If you've got 100 grams of solution, 20 grams is HCl. So that means you have 80 grams of water, and you need mass for if you go into molality here. So then you take your 80 grams of water and go to kilograms. Okay, so it's going to be 10 to the 3rd grams per kilogram, so that's going to be 0.080 kilograms. Then you can put that together. Molality will be equal to 0.549 moles HCl divided by 0.080 kilograms water. And that number is 6.9. Second part, your 20% by mass solution now. 20% by mass going to molarity. And you're going to have 100 grams of solution. Use the density 1.5 grams per mole. And then you have 1,000 milliliters in a liter. So this is going to be 0.067 liters. That's the volume of the 100 grams of solution. Molarity then is 0.549 moles divided by 0.067 liters. So it's 8.2. Then the third one, you're going 20% by mass to mole fraction. Okay, and you got 80 grams of water. Go to moles, 18.02 grams per mole, 4.44 moles H2O. And you got it all then. You got 0.549 of the moles of the HCl. So mole fraction of HCl, 0.549 divided by 0.549 plus 4.44. Mole fraction of HCl, 0.11. Do the same for the water, and you're going to get water. Mole fraction of water would be 0.89. The sum of the two is 1. Okay, so when you're reviewing this again, you can probably skip some of this. Go back and put it all in that chart, and you'll see some similarities and differences. It helps to kind of organize your thinking on it. All right, anyway, so this last big topic here is colligative properties. And these properties, like the ones given here, freezing point, boiling point, and osmotic pressure, these values are different if you have a solution versus a pure liquid. And so the amount of change between those two, the pure solvent and the solution, in other words, how does the freezing point change, depends on the number of particles in the solution. So we're going to talk about all three of these. All right, I'll just do it here. So there is a term called the Van 't Hoff factor. It's given the symbol I. And so if you have, let's say if you have an ionic compound like HCl, let's say you have a 2 molar HCl solution. So you know that to be a strong acid, so it's going to completely dissociate. We say that this molecule has a Van 't Hoff factor of 2 because the molecule of HCl dissociates into 2 ions. So when you dissolve this in water, you have 2 molar H plus and you have 2 molar chloride. So in 1 liter, you have 2 moles of H plus and 2 moles of chloride, so a total of 4 moles in solution. And so the change of the freezing point or the boiling point depends on that number. Okay. So let's see, just one more example here. If it's a covalently bonded molecule, it's not going to break up into ions, so I will be equal to 1. And then if you had something like H3PO4, what does that break up into in solution? 3 H pluses plus a phosphate, right? So there's a total of 4 particles. So I is equal to 4 for that. All right, I went ahead. I should put that slide right next to this one next time around. Anyway, we're going to look at these 3 effects, and 2 of them are directly related. First 2, freezing point and boiling point, are related. Freezing point depression and boiling point elevation are related. So this is a graph that was just shown at the end of the last chapter, and we're interested in what's happening for pure water. This part right here. And comparing that to a solution. So what you want to get from this graph is that for H2O at 0 degrees C and pressure of 1 atmosphere, that will be the melting point right there. So the melting temperature is 0 degrees C for pure water. The boiling temperature, this is the liquid to vapor equilibrium. So the boiling temperature is 100 degrees as long as it's atmospheric pressure. So the boiling point and the freezing point change when you start adding solute. Here, let me go. And this is what it looks like. So it's a little bit of an exaggeration on this slope right here, but that's okay. And so what happens is that there's a lowering of this curve when you have the solution. These parts right here. And what it means is that if the freezing point, so this is the solid to liquid transition here. If the freezing point is at 0 degrees for 1 atmosphere, then for the solution, it's moved over here. The solution freezing point is here. It is less than pure liquid. It's less by a couple of degrees. So let's see, we could say that right here, the freezing point of water, maybe we would use that symbol. And then this might be the freezing point of the solution, make it prime. Okay. And then the difference between them is delta T. So the difference between these 2 temperatures is delta T for freezing. And that depends on the number of particles and other things. Now, I like this graph very much. Most of the books don't put them together, the boiling point and the freezing point, but they are intimately related here. So if you have 1 atmosphere, the boiling point of water is 100 degrees, right? And it's where this curve crosses the 1 atmosphere line. And then for the solution, you can see it's way over here. Right, that line continues, that curve continues. At 1 atmosphere, the boiling point of the solution is way up here. So let's go ahead and call 100 degrees C the boiling point, boiling temperature for the pure solvent, water. And then T, let's call this one TB prime. Well, I guess they use capital here. TB prime, doesn't matter. Okay, and that would be the symbol for the solution. So the difference between these 2 is going to be delta TB. It would be TB prime minus TB. And so the fact that it even happens, number 1, but then you look at, the degree to it, or the extent to which the temperature has changed. This is this delta part right here and here, and that, is useful information for making solutions. All right, so let's see what we got here. This one gives you the equation, and it is this one right here. So the delta T, the difference between the 2 freezing points, is equal to Kf, and Kf is a constant. It's called the freezing point depression constant. 1.86 degrees C per molal. And then times the molality. I told you we were going to use that. And then I is the Van Hoff factor. So if that Van Hoff factor were 4, then it would be 4 times what it would be if the Van Hoff factor was 1, right? So if it breaks up into particles, you get a bigger freezing point depression. And then the other one here is the boiling point elevation, which is similar. Except for the constant, just different here, KB. This is the boiling point elevation constant, and it's equal to 0.52. So it's about, if you look at those two numbers, it's about a quarter of KF, approximately. All right, so these are the constants. M is molality, and I is the Van Hoff factor. So there's the slide that I was waiting for. I should have put that earlier. I will be equal to 2 for sodium chloride. I will be equal to 3 for calcium chloride. I will be equal to 4 for sodium phosphate. And I is equal to 1 for ethylene glycol. This is the one that's got covalent bonds. And it doesn't break up into ions at all. Okay, so now I think we're ready to do this problem. And let's see, we're going to calculate the boiling point and freezing point of the solution. So this is going to be TB prime and TF prime of a solution containing 39.5 grams ethylene glycol, which is this organic molecule shown in parentheses, dissolved in 750 milliliters of water. Assumed density of water is 1 gram per milliliter. All right, so we can first of all calculate the molality of the solution. Probably a good place to start there. So M will be equal to 39.5 grams. I'm just going to say ethylene glycol like that, ETG, ethylene glycol, rather than writing that out. But you got to go through to get the molar mass to be, there's 2 times the mass of carbon plus 6 times the mass of hydrogen plus 2 times the mass of oxygen. When you do that, or you could just Google it, it'll be 62 grams per mole per ethylene glycol. And then you're going to divide that by, let's see, we'll have to, since the density of the solution is 1, 750 milliliters will be equal to 0.750 kilograms of water. So this is going to be equal to 0.849 molal. All right, put that together with the equation for delta T freezing point depression, 1.86 degrees C per molal times times 0.849 molal, and then I in this case is going to be equal to 1, and I think that's all we need. So this will be equal to 1.58 degrees C. So if you remember on the graph, the freezing point of the solution was to the left of the freezing point of the pure solvent. And so you can say that delta TF is 0 minus TF prime, 0 being TF, and this would be 1.58 is the depression, 0 here, minus TF prime, solve for TF prime, and that's going to be negative 1.58 degrees C. All right, so relative to 0 degrees for the freezing point of pure water, goes down about 1.5 degrees. If you increase your concentration, you could get a pretty dramatic effect there. Okay, and then you have delta TB. And so for this, you've already got the molality. It's the same molality, which was the 0.849. This time you're going to use the boiling point elevation constant, which is 0.52. And that'll be degrees C per molal. So that'll be 0.849 for the molality times 1. So delta TB is equal to 0.44 degrees C. So delta TB, if you remember, the boiling point, since it's an elevation, the boiling point of the solution is greater than the boiling point of the pure solvent water. So delta TB then will be equal to TB prime minus TB, which is going to be 100. So you solve for, well, got to plug in first the boiling point elevation, 0.44 degrees C. That's equal to TB prime minus 100.00. Put some decimals in there, I guess. Solve for TB prime, the boiling point of the boiling temperature, the boiling point of the solution is going to be 100.44 degrees C. So that's not a dramatic effect there. I guess you could say it's about approximately a quarter of the freezing point depression. But again, if you have more than 39 grams of ethylene glycol, you could have a pretty dramatic effect. And ethylene glycol is a really good example because that's what's used in antifreeze. And the principle of antifreeze, you'd have to have a lot more than this mass, but still the principle of the antifreeze is that if you put it in your car coolant system, then you can take your car down to much lower temperatures. Maybe you want to go skiing and you go up into the mountains where it's below freezing. The question is the fluid in your car going to freeze? And the answer would be no. If you've got ethylene glycol solution, it will freeze at a much lower temperature and you'll survive up there. Your car will make it through the cold. But you could take that same solution and drive out into the desert on a hot day, and you have the effect that the boiling temperature for the solution is higher, so you could take your car out to much higher degrees than 100 degrees C, and it wouldn't boil over, right? It would not boil. I would say the weather is not going to be that high, but your engine can get that hot, and it can get up to the boiling point of water. So this kind of temperates the effect, and you can take it up to higher temperatures without it boiling over. All right, so that's a very interesting and useful colligative property. And then the third colligative property here is osmosis. It's different. Osmosis is the tendency of water or ions to flow through a semi-permeable membrane in order to dilute a more concentrated solution. And you can see this in this figure here. Okay, so you've got a beaker, and you have in there some kind of container that is permeable or semi-permeable to molecules and ions. In this case, you've got some salt water inside, and the water has the ability to go through the material of this flask, some kind of plastic maybe. Water can go through, and it will do so. The thermodynamic tendency here is for the solution to become more dilute, and more and more water will flow in. And in principle, this gets so dilute that the concentration of water is equal to the concentration of water in this solution. So it dilutes until the concentrations are equal. That's the osmotic force. So this next diagram shows that, let's look at the diagram first and then I'll give you the definition here. So you got two chambers in this one. This one has a concentrated solution and a dilute solution. There is aqueous. And in this case, the water can flow back and forth. So the tendency will be for the water to flow from the dilute solution into the concentrated solution in order to dilute this one to the point when their concentrations are equal, which is pretty much what you've got here. A little bit of a differential, but I think at this point they're supposed to actually have the same spacing between the dots to make the concentrations equal. So the water will flow until the concentrations are equal, and it basically has lost a lot of water in that process, and then on this side, water's been gained. So you can just hold a meter stick up to this tube, or you put it in the middle here. You have a meter stick, and you can measure the height. It's like a manometer. And the definition of the osmotic pressure is the amount of external pressure. You put a plunger here. You start applying pressure. The amount of pressure that's needed to force that water back to what it was originally over here. Okay, and H then has another symbol, pi, and that's going to be the osmotic pressure. So you have the osmotic pressure, osmotic pressure, the height that you measure, which we're going to call pi, the pressure applied to force the solutions to have equal volume after osmosis has occurred. And it's just like PV equals nRT. In this case, well, it's not written that way in particular, but you could say pi V is equal to nRT, and then you want to multiply it times I, because the osmotic pressure on the left here is proportional to the number of particles per molecule as well. All right, so then if you divide both sides by volume, then you have pi is equal to n over v RT times I, and then you recognize here that you got moles per volume, per unit volume of solution, so that's molarity. So pi is mRT, and oftentimes the I is actually in front there. It doesn't matter. And that's the one that we have up here. And, different forms of that. You can use mass instead of moles and things like that. So then, until do a calculation on this next slide. And this is for hemoglobin. Hemoglobin is a non-electrolyte. If it's a non-electrolyte, then it's not going to break up into ions, right? So that means for hemoglobin, I will be equal to 1. So here you can weigh out 5 grams of the hemoglobin, put it in 1 liter, measure the osmotic pressure, and it's in atmospheres, by the way. If it's in torr, you have to convert to atmospheres. 1.8 times 10 to the minus 3 atmospheres. Temperature is 298, and you want the molar mass. So molar mass, you can use capital M for molar mass. This is going to be equal to grams per mole, right? So this is going to be mass divided by moles of hemoglobin. And the moles, well, we already know we have 5 grams of hemoglobin. Now we want to know how many moles that corresponds to. And if we know the moles, then we can calculate the molar mass. So you can use pi V is 1 times nRT, and calculate the moles N. So it's going to be PV divided by RT. And here you have 1.8 times 10 to the minus 3 atmospheres. The volume is 1 liter. You divide by R. In this case, you got to use and times 1 for I. So for R, because it's liter atmospheres, you got to use that unit in your constant. So 0.08206. Liter atmospheres per mole Kelvin. And then 298 Kelvin will give the moles. So N is 7.36 times 10 to the minus 5 moles. So you got it, and now you just plug it in right there for molar mass. And molar mass will be 5 grams divided by 7.36, 10 to the minus 5 moles, and this is 6.8 times 10 to the 4th grams per mole. Now, do you think that is a reasonable number for molar mass for hemoglobin? The answer is yes. Those molecules are absolutely enormous, and that's reasonable to have 10 to the 4th grams in 1 mole. All right, that's an example there. Now we finish by just making a few comments for osmotic pressure for cells. when you're in the hospital and you need an IV, you better make sure, or your doctor better make sure, that the osmotic pressure of the solutions is the same as the osmotic pressure inside your cells. So if that's the case, then there's going to be no tendency for the water in the cells or the water in the solution to be moving in and out of the cell wall and cell membrane, I guess I should say. And so if they're equal, then that's going to be an isotonic solution here. In the case where the solute concentration from your IV is greater than the solvent concentration in your cell, then, so let's see, this concentration outside, so water will flow, getting tired here. Water is going to flow out in order to dilute the concentrated solution on the outside. And so the cells will shrink as a result of that. That's hypertonic solution. If it's a hypotonic solution, then you've got the concentration inside is greater than the concentration outside. So the water is going to flow into the cell in order to dilute this concentrated solution. So water is going to flow in. You might get to the point where the cells burst. So that's why you got to have an isotonic solution for your IV. It's a good example. Here are 3 pictures in red blood cells. This is, the term is a little bit different, but they mean the same. Osmotic. Anyway, this is like isotonic. And this is what a normal red blood cell looks like. If it's taken in too much water because the solution inside was more concentrated. No, I got it backwards here. It looks like it's gonna, no, I had it backwards, sorry. I was misreading the picture. So this is the one where it's shrinking, meaning that the water has left the cell and gone into the solution to dilute it. And then here's the third case where water has to flow into the cell because the concentration inside is greater than outside. All right, that is the end of the chapter, and it's the end of the course as well. So hope you guys have a great day.